So today the topic is about SeaBIOS or the CSM on physical hardware. I think many people and companies have been using SeaBIOS on virtual hardware for many years. This one is for the first time that we can use SeaBIOS or the CSM on physical hardware. Actually, we spent about 4 weeks to make it happen. I think it's difficult to do this, but it's not that difficult. So first thing first, what is the CSM? So CSM is the abbreviation of compatibility support module. So on UEFI BIOS, to support legacy boot, to boot a legacy bootloader or legacy OS, we need the CSM. Otherwise, the legacy stuff cannot talk to UEFI BIOS directly. Here is the 3 different types of boot. So the easiest one is on the bottom, is the direct boot. If we configure the Linux kernel with the EFI stub option, then the UEFI BIOS can directly boot the kernel because in this way, the Linux kernel itself is a UEFI application. The middle one is the UEFI boot. This is the most common and the regular one. Basically, the bootloader is also a UEFI application. So the bootloader can talk to the UEFI BIOS by regular boot services. And then the bootloader can get all the system information and finally load the OS. The top one is the most difficult one because the bootloader is legacy. It doesn't understand the UEFI stuff. So it has to depend on the CSM. We call it the CSM system because it runs in the system bit mode. So the CSM system is what we it's the one we can replace with the SeaBIOS because SeaBIOS itself is also the system bit in the system bit mode. So basically, in the BIOS side, we have some legacy modules. These modules will talk to the CSM, and the CSM will do some initialization, and then finally it can load the OS. So in the next slide, we will have details about how the UEFI BIOS and the CSM they talk with each other. So in the BIOS, we have a bunch of protocols, and they communicate with the CSM and pass down the system information to the CSM. And the CSM will set up some tables and services that will be consumed by the legacy bootloader. And you can see that in the all the communication, the last step is the boot. The last step boot is the one way. So once the BIOS pass down the execution to the CSM, it will never return to the BIOS. The only way we can return to the BIOS is through the SMI. We will cover this in the next few slides. So this is all the changes we made on SeaBIOS. I think we have more than 10 changes. We will go over all the changes one by one in the next slides. So the first change we made is about PCI bus numbers. So by default, SeaBIOS only supports single root. That is the PCI bus number 0. But the physical hardware may have multiple PCI roots. For example, the Intel Xeon server CPUs may have more than 6 PCI root ports. So we made the change to make the SeaBIOS can support all the PCI bus numbers from 0 to 255. The second change is also about the PCI. So SeaBIOS probes all the PCI devices during the communication between the SeaBIOS and the UEFI BIOS. So somehow the SeaBIOS probes the devices too early, so that not all the PCI devices are available yet. So we made the change to move the probe function a little bit late to make sure all the devices are ready. Then they can be probed and initialized. This one is about PCI option ROM. Actually, SeaBIOS supports PCI option ROM, but SeaBIOS doesn't add the PCI option ROM to the boot list. So in the end, we cannot boot from the option ROM. So we have made the change to add the PCI ROM to our boot list, so we can boot from the option ROM, either as a BEV or BCV device type. This change is also about PCI option ROM. So we found that even SeaBIOS probes the PCI ROM, the PCI option ROM, and check the signature. And if the PCI ROM is valid, it will add to the PCI ROM list. But when the PCI option init function is called, and if the init function calls some time services, for example, if the init function want to do a delay, and then the init function will hang because we found that the SeaBIOS doesn't initialize the timer and the clocks before the init function is called. So basically, the clock and the timer initialization is too late in SeaBIOS. So the change we made is that we move the clock and the timer initialization a little bit earlier to make sure before the init function is called, the timer service is ready. And also, one thing we have to make attention is that for the PCI option ROM init, it's a one-by-one style. That means when the PCI ROM init is called for one PCI device, it will return to the BIOS. So next time for another PCI device option ROM, we have to do the clock and timer initialization again, because once we return to the UEFI BIOS, all the clock initialization were done in SeaBIOS has lost. So we have to do it for every PCI ROM dispatching run. This one is also about the PCI option ROM. I think on the virtual platform, because we either have no PCI option ROM at all, or at least we have one. So the 120K PCI option ROM memory size should be big enough. But on physical hardware, because we may have multiple PCI option ROMs, and it can consumes up all the 122K memory. So we have made the change to shrink the runtime SeaBIOS memory to free up the E segment, which is 64 KB. So this can make sure that we can support multiple PCI ROMs. This is especially required on some servers that we have multiple PCI cards. Since SeaBIOS runs in 16 and 32-bit mode, so it is possible to access 64-bit MMIO, but sometimes the BIOS may assign 64-bit address to the PCI bar. So this will make some PCI device drivers in SeaBIOS doesn't work. So the change we made is that we added a SMM driver in the BIOS, and from SeaBIOS side, we used the SMI to trap into BIOS, and the UEFI BIOS will do all the 64-bit register access and bring back the results from UEFI BIOS to SeaBIOS. So this way we can do the 64-bit memory access. The downside is that we have to include the SM driver in BIOS. So the change is not very straightforward. But anyway, we can do the 64-bit access. This change is about the hard drive support. So by default, SeaBIOS can only support up to 2 hard drives. This may have some issues on real hardware because on we may have more than 2 hard drives to boot, right? So the limitation comes from the PDA slots for the hard drives. We only have 2 slots in the PDA area, and SeaBIOS only do the one-time initialization to the PDA slots. So after that, we cannot change it anymore. So the change we made is that we don't do the one-time initialization. Instead, we map the hard drive dynamically. So for each attempt to boot one drive, we just do the mapping. And if the attempt on one hard drive failed, and if we want to try the next hard drive, and then we will remap the hard drive one more time. So this way, we will not have the 2 slot limit in the PDA. So we can actually support unlimited hard drives. This is a new feature because by default, SeaBIOS doesn't send back any boot events to UEFI BIOS. As I said earlier, the only way that we go back to UEFI BIOS after the boot is started is through the SMI. So we have added 2 boot events in the SeaBIOS. One is the boot started, another one is the boot error. So we can send these 2 events to BIOS through the SMI. So the UEFI BIOS can get the 2 events and finally log them to the BMC, because this is required for typical data center servers. We need to log all the boot events, either it's a success or it's a failure. This one is that we will have to disable the PS2 port because when we are using the SeaBIOS or the CSM on physical hardware, we found that if we keep the PS port option enabled, but on hardware, we actually disable the PS port. That means the hardware is not present. So this way, we will get some, junk data in the keyboard buffer. And finally, if the bootloader will check the KBD buffer, and the junk data will be make some issues. For example, the grab will pop up a menu as if someone pressed a key from the keyboard. That's because the junk data. So the change is that we have to disable the PS2 port option if we disabled it from the hardware. Otherwise, it will make troubles. The last change is about the package boot. So basically, it's the issue comes from the PMM. PMM is the memory allocator in SeaBIOS. So if we download a big RAM disk, for example, larger than 800 megabytes, the the Pexy, the Pax Linux or Sys Linux will hang. That's because the SeaBIOS cannot find a buffer from the PMM pool, because the PMM pool is a path from the UEFI BIOS to SeaBIOS, and if we tell the SeaBIOS that the pool started from below the 16 megabytes, and also if we have fragmented E82 table, the SeaBIOS could fail to find any usable memory from the below 16 megabytes address space. So the solution is that we have to pass down the PMM up limit of below 4 GB instead of below 16 M to the SeaBIOS to make sure the SeaBIOS can always find usable memory to service the big allocation request. Yeah, so I think that's all the changes we made to make it happen, to make it work on the real hardware. And so far we didn't push all the changes to SeaBIOS units yet, but we have planned that we will push all of them by December. So once that was done, then everyone should be able to use SeaBIOS as a CSM on physical hardware. So we are really excited to see that happen. I think that's all for today. Thank you very much.